Good morning, chemistry students. Today we are officially getting into how to write electron configurations. So we're looking at standard 1G specifically, where we are using models including electron configurations to predict chemical properties. So today we're just going to see how to write and or draw some of the different types of electron configurations. So electron configurations, think of it as we are giving each and every electron an address. They live in this giant cloud that is like a really big hotel or apartment complex or whatever you want to visualize. But every electron has to have a place to go. And what we're doing when we're writing electron configuration is we are actually giving the specific address for all of the electrons' locations. So we have three different types of electron configurations that we can do. Today we're looking at the first two, which is the extended or the complete electron configuration, and the arrow or orbital diagrams. So reviewing what we saw yesterday, you're going to want to make certain that you do know this information so that moving forward, you're able to answer some kind of constructive response questions. Plus, knowing your orbitals, max number of electrons, and position on the table, on the periodic table, will make your life much, much easier as we are getting further into this particular concept. So my S sublevel, as we saw the other day, each energy level is broken up into different sublevels. The higher the energy level, the more sublevels that are present. So my first and lowest energy sublevel is the S sublevel. In terms of shape, we just call it a sphere. So if I were to draw it, I draw a circle. So if I'm looking at a model for the S sublevel, it kind of looks like a balloon. So the balloon, the air in the balloon represents where the electrons are likely to be found. And the nucleus is in the very, very center. It's just a teeny tiny little dot in the center. And the air is where my electrons live. On that sphere, no matter which way I turn a ball, it still looks like a ball. There's no obvious way to do orientations. So therefore, my S sublevel only has one orbital. The thing to note about orbitals is that every single orbital can hold two electrons. So this little sphere right here representing the S orbital would hold at most two electrons. Now, when we're looking at our periodic table, it can give us a hint as to what orbital and what sublevels are being filled. So if we happen to be looking at groups 1 and 2, groups 1 and 2, the last electrons that are being filled are the S electrons. So S1 and S2. So S1 just means one electron in here. S2 means that there's two electrons in there. So my P sublevel, it's called a dumbbell shape. When I draw it, to me, it looks like an infinity sign or a figure 8. But if we were actually to see it in 3 dimensions, it looks kind of sort of like this. So the lobes, the balloons represent where the electrons are found. My nucleus is in the center. And I can actually turn this 3 different ways because we're talking about 3 dimensions in space. So I can have it like this, left to right. I can have it like this, up to down. And I can have it like this, in and out. So those 3 different orientations let me see and let me know that I have 3 different orbitals. Well, if I've got 3 orbitals, each orbital can hold 2 electrons. So every single orientation can hold 2 electrons. If there's 3 orientations, and that means we can hold 6. So my P sublevel is a little bit more complex. It's a little bit harder to get into. So therefore, it has a little bit more energy than S. In terms of position on the periodic table, if we happen to be in groups 13 through 18, we are filling up our P orbitals. I will actually show you what all 3 P's together look like in just a second. It's just I only had a limited number of balloons today, so I got to show you what the D looks like before I put my 3 P's together. So my D sublevel, in terms of shape, we call it a four-leaf clover. It's kind of, for the most part, like two p orbitals overlapped. So not the best drawing, but that very, very center where all the lines overlap, that would be my nucleus. I'm making it kind of bigger than it probably should have. That nucleus, we're not likely to find electrons there. But the empty spaces represented by the little circles or the lobes, that is where we're likely to find d electrons. There are 5 different orientations. I don't know if you're noticing, but this is a pattern. It goes up by odd numbers, 1, 3, 5. So there are 5 different orientations. And if I were to look at the D sublevel in 3 dimensions, one of them looks kind of sort of like this. So four-leaf clover, you can kind of see that four-leaf clover orientation. There are 4 of them that look exactly like this, and they align themselves along the different axes. So let's see if I can do this. We have up and down, left to right, and then they kind of go cattywampus in between each of the axes. There's a 5th one that doesn't look like any of the others, but don't worry about what it looks like. It just know there's 5, and that most of them look like this. So I promised to show you all of the p orbitals together. Second, do a little bit of balloon origami, and ignore the fact that I got one brown balloon. Just ran out of blues. So if I were to look at the P sublevel, those 3 P sublevels that I showed you earlier, and I put them all together, this is what it looks like. 3 dimensions. We have up and down, left to right, in and out. My nucleus is in the center. So those little balloons represent where the clouds can be. All right, back to D, my D sublevel. It has 5 orbitals. Well, with 5 orbitals, it can hold at most 10 electrons. And D takes more energy to get into than your P. So it is a higher energy level. And our D sublevel, in terms of where we find it on the periodic table, or the D block on the periodic table, we find it in groups 2 through 12. All righty, last but not least, F. It is the most complex. I'm not going to show you an illustration. You're not going to be asked to identify an illustration, so just don't worry about that. If we continue with the pattern for the number of orbitals, 1, 3, 5, well, the next odd number is 7. If there are 7 different orientations, that means we can have 14 electrons, and F is the highest sublevel that is used with our current elements when the elements are in the ground state. So where do we find our F electrons? It is the inner transition metals. So those bottom 2 rows that aren't attached to anything, the lanthanide and actinide series, that's where you find your F electrons. Those are the elements who are filling up the F sublevel last. So if I were to take and look at my periodic table and kind of put all this together, this is a great graphic to actually have as you're doing electron configurations, because not only is it telling you where to find the different sublevels, but it's also giving you an indication of the energy levels. Remember, energy levels equals the periods, and periods go across the periodic table. They are my horizontal rows. We have 7 periods. Each period represents a different energy level. My groups, changing colors, are the ones that go up and down. Those are my vertical columns. And I'm just gonna, yeah. you go. So those are my vertical columns. When we're writing electron configurations, the way we indicate a energy level is with a large number. And when I say large number, I just mean like visually large. So big 2 versus an exponent, which is a smaller representation of a number. By large, I don't mean like a million. Our numbers are going to be 1 through 7, or well, technically 1 through 14. But anywho, so my sublevels, those are my different blocks of the periodic table. Sub-level and blocks are interchangeable. We represent sublevels with letters. We use it with a lowercase letter. So my S block on this particular graphic are all light blue. Primarily, it is column 1 and 2. Helium is an odd exception. We'll talk about it when I get to configurations. I'm going to actually do it as an example. But you can kind of pretend that helium is over beside hydrogen, and it makes sense visually. So the right side of the periodic table is my P sublevel. My D sublevel is that transition metals, and my F sublevel, that's that inner transition metals. On our class periodic table, I have a visual, like empty boxes, gives you the numbers to kind of remind you to go down there. But if you do look at our class resources on page 2 or 3, you do have an extended periodic table that actually puts everything all neat, nice, neat, and pretty together. So orbitals, to figure out the number of orbitals by looking at the periodic table, once you know the blocks, you can figure out orbitals. So if you know that groups 1 and 2 are your S block, well, 1 and 2 is 2 columns. Half of 2 is 1, so there's 1 orbital. 13 through 18, well, that's 6 columns. That's my P block. 6 columns means there's 3 orbitals, because we can fit 2 electrons per orbital. And think of a box on the periodic table as representing a single electron. So the thing about our orbitals is that they do have 2 electrons per orbital. And if we were drawing and illustrating individual electrons, as we saw with introducing our rules the other day, we always represent them with opposite spins when they're put together. So my electrons, if I'm not drawing them, we represent them as an exponent. So if I kind of put all this together, if I put energy level, sub-level, and electrons together, we get a big number, a little letter, and an exponent to represent a total of 2 electrons in the first energy level, in the first sublevel, or S sublevel. So in terms of how electrons arrange themselves in that cloud, in that house, hotel, however you want to think about it, the electrons always have to go in that first energy level first. You will notice that I will always start at the top of the periodic table. The reason is the top row of the periodic table is representation or representative of that first energy level. So if you think of it as electrons being lazy humans, I always love using the analogy of a lazy teenager. So picture somebody you know who is just like really, really lazy, and make them even worse. And then you've got the motivation of an electron. So electrons aren't going to go to another energy level unless they absolutely have to. They don't have the energy to do it naturally, so they're going to go in the lowest possible place. Electrons are going to spread out before they pair up. So we don't see this in every single sublevel. We only see it in the P, Ds, and Fs. But in terms of my electrons, if I look at a single P orbital, yes, it can hold 2 electrons, but there are 3 of them. So first electron goes in the first P orbital, second electron goes in the second P orbital, third electron goes in the third P orbital. Now, P can hold a total of 6 electrons. So then I go back and I start spinning upside down, filling in the P orbital completely. So think of this, if you've got siblings, you'll get this analogy. Think of this as like sharing a bed with a younger brother or older brother, whatever, sister. You don't want to pair up with your sister, your siblings. You want your own space if at all possible. If it's not possible, then yeah, you're going to pair up. So think of it that way. And we can only hold 2 electrons in a single orbital. So if we think it through with what we saw the other day, we saw that the first energy level only had the S sublevel. It only had the S sublevel. Oops. Therefore, it only had one orbital because S always has one orientation, one orbital. So in that first energy level, we can only hold 2 electrons. My second energy level, oh, bad nabbit. Okay. I love technology. We love technology. There we go. Okay. Apologize for that. Thought I had something set up the right way, and it did not. So the second energy level, we saw yesterday that on the second energy level, you can find the S and the P sublevel. The S sublevel has 1 orbital, the P has 3, so that is a total of 4 orbitals, which means my second energy level can hold 8 electrons. Third energy level, we have S, P, and D. S had 1 orbital, P had 3, D had 5. Again, those odd numbers. So if I add all that up, I get a total of 9. 9 times 2 gives me 18 because each orbital can hold 2 electrons. These numbers should be sounding familiar because these are our dots in our Bohr's model. So remember drawing Bohr's model the other day? Those dots to represent the electrons, the number of dots per ring. This is that same overlap. So Bohr was partially correct in the fact that he had electrons and energy levels. They don't live in a ring, but they do occupy energy levels. So if I were to look at that second ring, it would have 8 dots, to a maximum of 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to draw the third one, but the third one will have a maximum of 18. And the fourth one, so it has S, P, D, and F, and they have respectively 1 sublevel, 3 sublevels, 5, and 7. So if we add all those up, we get 16. There are 16 different orbitals. 16 times 2 is 32. Yeah. Sorry. Mental math. Yep. So yesterday, we also introduced the rules that we're going to be using as we write these electron configurations. Aufbau's principle is the rule that we use every single time. Aufbau says that we always start at the lowest energy level. Not only do we always start at the lowest energy level, so the first period, but we also start with the lowest energy sublevel. That means we're always going to fill S before we get to P. We're going to fill P before we fill D, respectively. So Pauli exclusion principle, Pauli exclusion, Pauli was the one who determined that there were 2 electrons in an orbital, and that when you have those electrons, they have to have an opposite spin. So one is spinning one way and the other spinning the other way. So not only are they spinning, but they're zooming all over the place as they're spinning. They're moving around within their little orbitals. Now, again, drawing electrons, we represent that opposite spin with arrows. So an up arrow means spinning one way, a down arrow means spinning the opposite direction. So Hund's rule, Hund's is the don't want to share a room rule. Electrons will spread out before they pair up. So, imagine you're the new kid at a school, first day on the bus, and you're not very social. Well, you get on the bus and there's an empty seat, you're probably going to go sit in that empty seat. All right. You have a choice. You don't want to share a bedroom or a bed with your brother or sister. You're going to spread out before you can pair up. Now we only visually see Hund's rules being used with the P, D, and F sublevels. So we don't always see it being used, but it is always there. Oops. So if you happen to have a printed periodic table, draw boxes and label them around the blocks of the periodic table where you find the different sub-levels. So my S electrons are groups 1 and 2 plus helium. My P electrons are groups 13 through 18. D are the transition metals. And F, this is the little reminder we have on ours, and it's that yellow piece trying to remind you that those F electrons actually fit in up there if we were to put everything together in terms of normal. Now, when we learned Aufbau's principle yesterday, I mentioned that there's some overlap in energy levels. That in terms of how much energy it takes to get into certain places, sometimes we saw some surprises. The good news is we can actually see those surprises in our periodic table. Bad news is you always have to remember that your D block and your F block are special. Your D block, the energy level, so my number for my D block is always 1 less than the period. So I would take my row number minus 1, and that gets me the energy level for my D block. Same thing for my F block. My row or my period number, except for this time, we subtract 2 because they're doubly as special. So 1, 2, 3, 4, 5, 6, 7. So I'm going to use 5, the 5th period, as an example. In the 5th period, we will fill 5s electrons before we fill 4d. Notice in terms of periodic table, if I'm counting each element in order of number, we get to 37, 38, and then 39. So 39 is my transition metals, and at 39, we are going to go to 4d. It is always 1 less than the period. So kind of the same idea with my intertransition metals. The only difference is we drop down 2. So if I look at that last period, we will fill the 7s before we fill 4f. I'm at 5f, and before we fill 6d. So in terms of filling up the cloud, treat it like you're filling in or coloring in the periodic table. We don't skip around when we're coloring in or filling in the periodic table because we are lazy electrons. Okay, so actually writing electron configurations. Electron configuration, as I said earlier, is kind of like giving an address for every electron. It's a way of notating where the electrons are in the cloud. The way you do it is you write a large number for each energy level. You use a letter for the sublevel and an exponent to indicate the number of electrons. So for example, if I were to look at oxygen, oxygen element number 8 has 8 electrons. Those 8 electrons are going to each have to have their own little place to be in. Well, electrons are lazy, so the first 2 are going to go in that first energy level. The next one, because that first energy level is now full, are going to have to go to the second energy level. Well, when we get to the second energy level, we now have 2 areas to choose from. We have S and P. So S is easier to get into than the P. That is why you will see 2S before 2P. Now, it is interesting to note that if we add up the exponents, 2 plus 2 plus 4, that will always give you your number of electrons. So it's a nice kind of self-check to see, are you where you think you are? Or if you get lost in writing configurations, it's a good way to see, okay, where am I in terms of filling up the cloud? What electron am I actually on? All right. So I was going to explain why helium is kind of weird. So we know that our first energy level only has the S sublevel. And this is why helium is weird. So hydrogen, having only one electron, would have an electron configuration of 1s with a 1 as an exponent. It has one electron in the first energy level in the S sublevel. So we read that as 1s1. But helium, we knew from Bohr that the S subshell, sublevel, could hold 2 electrons. So helium being in that first period and having only 2 electrons is going to fill up the S sublevel. So that second electron is going to go in there and fill it up before it ever goes anywhere else. So helium doesn't have p electrons because it doesn't have enough electrons to get that far into the cloud. So helium, if we cheat and pretend it's on the other side of the table, we can kind of see how our periodic table is a tool for writing electron configurations. So what I would do is I would write the row number and then the sublevel. Oops. So my sublevel is my S, P, D, or F. And then I count the number of boxes that I have to color in to get to the next sublevel or the next period. So I'm going to use lithium as my next example. Lithium has 3 electrons. I know this because it is element number 3. So I'm going to go and try and fill in my cloud. If I treat the periodic table kind of like a cloud and I color in each of the elements as I fill in the cloud, it will guide me through it. So we always have to, according to Aufbau, start on the first energy level. My first energy level will always have an S sublevel. In that first row of the periodic table, if I were to color in my elements, I would see that there are 2 elements for me to color in. Therefore, my exponent must be 2. So I wrote the row number, the sublevel, and the number of electrons, or think of it as the number of boxes colored. Alrighty. No, I'm not going to go through and do every single element because it gets a little bit tedious, but this is the nice thing is we can kind of skip around. So I'm going to skip over to argon. Argon over here has 18 electrons. Argon has 18 electrons. That means we have to give the address for all 18 electrons. Well, according to Aufbau, the first electron has to go in the first energy level. So I've already colored that blue from the previous example, so I'm going to keep the light blue. 1s2. All right. So if I look at my periodic table, after element 2 comes element 3. Well, element 3 is in period 2, so that means I got to write a 2. It's in the S part of the table, so it means I got to write an S. And if I color in the elements that are in that part of the table, notice that there's 2 that I colored in, so my exponent is 2. After 4 comes 5. Now I am on the right side of the periodic table. We are going at element by element, line by line. We are in the second period still. So we are still in the second period, but now we're in the P part of the table. I'm going to color in until I get to either the end of the row or the element that I'm looking for. So I happen to be looking for argon, so I'm going to go all the way to the end of the row. That's a total of 6 boxes, 6 electrons. So I have to write 2p6. Yeah. All righty. After 2p6, I'm done with the second row. Now I have no choice but to fill in the third row. So I write the row number. I'm in row 3. I'm on the left side of the table, so I'm in the S block. Trying to get all the way to 18. So I color in until I'm done with that block. My exponent is 2. All right, still trying to get to argon. So on my way to argon, I'm still in the third period because this goes all the way across. But now I'm on the P side of the table. Color in the boxes, including the element that you want. So we want argon. That means I'm going to have a total of 6 electrons here. Do a quick self-check. Add up the electrons. 2 plus 2 plus 6 plus 2 plus 6 gives me 18. Argon has 18 electrons, so that is likely the correct configuration. All righty, so let's try a little bit of a harder one. This time we are doing xenon. Yeah. So xenon. Xenon, new element. Well, those first electrons can't jump straight to number 54. They have to always start in the first energy level, first period, first sublevel. That means we're going to go all the way back to number 1. We're going to use the periodic table to guide me in filling in the cloud. So my table tells me that element number 1, electron number 1, goes into the first period S block. Hopefully by now you're starting to see that every time you write an S, it's either going to be a 1 or a 2. Well, since I'm filling it all the way up, we know it's going to be a 2. After those 2 electrons, I have no choice but to go to the second period. I'm still on the left side of the table, so it's 2s. S's tend to get 2s, but I can see on the table that it is a 2. All right, number 4. After element number 4 comes number 5. Now I'm on the right side of the table, and I can see that there's a total of 6 elements over here. I am in the second period P block with an exponent of 6. And you know what? I'm going to actually do a quick on the fly change. We're not going to do xenon. We're going to do TE. So I apologize. We are actually going to do TE instead. Just because I just realized that I did 2 noble gas examples if I did xenon. So 2p6. So far, we have written the address for 10 electrons. We know where 10 electrons are in those clouds. Well, now we got to figure out where electron number 11 lives. To do that, I look at element number 11. So element number 11 is in the third period. It's in the S block. And if I look on that part of the table, there are 2 electrons. So after 12 comes 13. Well, if I number the outer side, I can see that, yes, I am still in the third row, but now I'm in my P block. So 3p, count the number of boxes, count the number of elements. That lets you know your exponent. All righty, we've now done 18 electrons. So now we have no choice but to go to electron number 19. Well, electron number 19 and element number 19 live in the same place in the cloud. So element 19 is in the fourth period. So fourth period S block. And if I look, there are 2 elements in that part of the table, so 4s2. Now, this is where that graphic earlier would be very, very useful. Because that graphic showed me that when I got here on the table that I was in the 3D part of the table. But if I don't have that graphic handy, I could just write myself a love note above the D block to remember to subtract 1 from the period. So my period minus 1. So instead of 4D, what actually comes next is 3D. But we get the exponent the same way. We still count the number of boxes or the number of elements in the D block. Remember, D block contains elements in rows 2 through 12. So it stops right there at the edge of the transition metals. If you count it up, it's a total of 10 electrons. Trying to get all the way to TE, because Miss Rains changed it up on the fly. So after 3D, we're now back in the P block of the table, but the P block's not special. So it's my row number, the sub-level letter, and then my exponent. So row number is 4, sub-level is P, and we're trying to get all the way to tellurium. So P6. This is messy, and I should have written smaller, but whatever. Continuing on, because we're still trying to get to TE, we now have 36 electrons accounted for. If you don't believe me, add up the exponents. After 36 comes 37. So we're in the 5th period, S block, and we can fit 2 electrons in that part of the cloud. Now we're back at our D block. Well, D is special. So instead of being 5D, it is 4D because it is 1 energy level less. Count your boxes, and you'll notice that it is an exponent of 10. All righty. Now we're in the last part of the configuration. We are actually filling in the last of the electrons. So these last electrons, we are in the 5th period, P part of the table, and I got to count the boxes all the way up to and including tellurium. So that would be 5P4 as the very last part of the configuration. Okay, so pause the video. You try these 2 examples. See how far you can get with the configuration. And I can tell you that both of these are easier than the one we just did. Okay. So fluorine, 9 electrons. We're going to give the address for all 9 electrons. So fluorine, electron number 1 goes in the 1st period, S block. And technically 1 and 2 can go there. So whether you put the helium where it belongs or helium where it doesn't belong, still 2 electrons in the 1st sublevel. 2nd period. My exponent tells me that I've only done 2 electrons, so that means I got to figure out where 3 is. Well, 3 is in the 2nd period, S block, and I notice that it's 3 and 4. So 2 elements. Moving to the next element on the periodic table. So we are going across the table, all the way to that right side. We are still in period 2, but now we're on the P side of the table. Trying to get to fluorine. 1, 2, 3, 4. Make certain you count fluorine. 5. My exponent is 5. Add up the exponents, I get 9. I have 9 electrons, so this is likely the configuration for fluorine. All righty, iron. Iron is Fe, it is not I. I is iodine. Fe is iron, it has 26 electrons. So the configuration is going to start exactly the same as the previous one. The only difference is this time we're going to keep going when we get to neon because we're trying to go all the way to iron. All right, after 10 comes the element number 11. Element number 11, electron number 11 lives in the third period, third row, the S part of the table, and there are 2 of them. Keep going, filling in the cloud, filling up my table, coloring it in. Next comes 3p. Count, total of 6 electrons. We're trying to fill in the cloud for iron. So keep right on going. After 18 comes 19. So I count up my exponents if I ever get lost and I see that, okay, I've got 18 electrons, so next must be 19. So I've got to be in the fourth period S block. And there's 2 electrons there. Trying to get to D. So I got my little reminder that D is special. I have to subtract 1 for D. There I go. Sorry, I forget that yellow is hard to see. So instead of this being 4D, this is 3D. So 3D, and I got to go all the way up to FE. 3D6. Whew. All right, that's a lot. But that is all of the electrons for the cloud for iron. So these are extended electron configurations. As I said, we were doing 2 today. So the other one is the arrow or orbital diagram. You can do either practice first. So start with the one that makes more sense to you. For some students, it's this one. For others, it's the boxes and the arrows. So the orbital and arrow diagram, instead of using exponents to represent electrons, we use arrows. And instead of using just letters to represent the sublevels, we use boxes. Oh, dyslexic moment. So arrow and orbital diagrams are very, very useful in the fact that they allow us to determine how many empty, full, or half-filled orbitals an element has. This lets us predict if an element is going to be magnetic or paramagnetic, which means it can be magnetized. It'll also let us predict if an element is more likely to gain or lose electrons just by looking at the arrow diagrams. So anytime we're drawing our arrow diagram and we're trying to represent the S sublevel, it gets 1 box. So usually it's represented with a box, and I always label it with its letter and its energy level. So 1S, 2S, so that 2 again is that energy level. So P always gets 3 boxes. So P gets 3 boxes because it has 3 orbitals. D gets 5 because it has 5 orbitals. F would get 7 if I were to ask you to draw it because it has 7 orbitals. So when we're using and writing our orbital diagrams, we still use the same rule. We still use Aufbau's principle, who says we have to start at the first energy level. Aufbau is the reason why Miss Raines keeps going back to element 1 on the periodic table. We always have to start with the first electron, first energy level, first orbital. Now, the things that we need to be mindful of now that we're drawing electrons is to spread them out before we pair them up. So we got to use Hund's rule, and we only really see it with P, D, and F sublevels. And when we do pair them up, we got to use Pauli's rule. So we got to give them an opposite spin. Now, the sum of my arrows would equal the number of electrons. Now, I'm going to go back to our fluorine configuration that we just did a few moments ago. And I'm going to turn it into an arrow diagram. If you're able to write the extended configuration, you can get the boxes and the arrows. I'm going to show you how to get it from this. We're going to erase iron because I need the place to write. So all righty. So fluorine, we had 1s2, 2s2, 2p5. So arrow diagram, if you write the extended configuration, anytime you write an S, it would get one box. Anytime you write a P, it would get 3 boxes. D would get a 5. Once you've got your boxes, then you just need to fill in your arrows. So my arrows equal the exponent from the extended configuration. Miss Raines always does up arrows first. It doesn't matter. Just be consistent. Do down first and then up. It doesn't matter. What does matter is when we get to this P sublevel, we've got to apply Hund's rules. So we've got a hotel room with 3 beds and there are 5 children. So there are 5 children. Child number 1 is going to go into the bed all by itself. Child number 2 is going to go into a bed all by itself. Child number 3 is going to go to a bed all by itself. Electrons spread out before they pair up. This is Hund's rule. They make their spins as large as possible. So all of those electrons are spinning the same way. But we got 5 electrons. We got 5 children. So we have no choice but to come back and start pairing up the electrons with that opposite spin using Pauli's rule. So electron 4 and 5, sorry, they're stuck. They got to share a bed. But that last one is all in its orbital all by itself. So you can get the arrow diagrams from the extended configuration. But let's say you don't like the extended configuration. Maybe it's not quite making sense. Well, then what I want you to do is I want you to draw your boxes on your periodic table. So this would represent my 1s box. This would represent my 2s box, continuing down. Here. Oh, and I forgot that I flipped the fictional table. So over here we have our P, 2P. And it gets 6 electrons. 3 boxes. So my first arrow diagram, I still have that first energy level. It gets 1 box because it's the S, and it gets 1 arrow because there's just 1. C, number 6, this is my fictional table. So C is not carbon. I believe it's chorsium. But either way, it still has 6 electrons. So we have to give the address and the position for all 6 electrons. So I could go through and just draw all my boxes and then go and fill them in. So 1s holds 2 electrons. So electron 1 goes in, electron 2 goes in. 2s can hold 2 electrons. 1 goes in, 2 goes in. 2p holds 6 electrons. This is the only reason I don't like doing it from the table, is many students think that you have to do this to begin with because they're side by side. But really and truly what happens is they are in completely different positions. So I'm going to color code it. Element number 5 is the blue arrow. Element number 6 is going to be the purple arrow. And it spreads out to this box. It goes up in its own box. So I can see that if I'm using 6 electrons, I'm going to need those many boxes. So I could just go ahead and draw my boxes and fill them in as I go. 1s, 2s, 2p. So S can hold 2 electrons, have that opposite spin. Electron number 5, arrow number 5 goes up, 6 up, 7 up, 8 down, 9 down, 10 down. That is Hund's rule. All righty. Well, next comes 3s. S gets 1 box. We're trying to get all the way to S. I don't have my fictional table, so I can't read that name. I think it's Solarium. So 2 electrons can go in there. Next comes 3p. P gets 3 boxes. If I count my arrows, I currently have 12 arrows. So arrow number 13 goes up, 14 goes up, 15 goes up. We're trying to do S, so I have no choice but to now pair up arrows for electron number 16. So it goes and pairs up with the first thing. It is a predictable pattern with electron configuration. If you want to, you can just write down in your notes the pattern for the energy levels and the sublevels, and then just fill them in as you go. Add your exponents, get rid of what you don't need. That is the really, really nice thing, is it's a predictable pattern. Alrighty. So you try the arrow or orbital diagram using the fictional table. So we're doing FZ, which is Phazon, and SU, which is supermanium. Remember, if you happen to be the PDF copy of the periodic table, you can use that Control F feature to find elements quickly. So Phazon has 12 electrons, supermanium has 14 electrons. First electrons have to go in the first box, first sublevel. Second electrons are electron 3 and 4. We're now in the second period, still in the S part of the table. I'm making my boxes too small. I promise it's an up arrow and a down arrow. Okay. Now we are at electron number 5, and I can see that electron number 5 lives in the same place in the cloud as element number 5 on the table. Element number 5 is in the second row, P block. So 2P. Well, I wrote a P, that means I got to draw 3 boxes. I can count on the table, and I can see that's on my way to Phazon. There are 6 electrons in there. First 3 go up. Next 3 go down. All righty. We have now done 10 electrons. So electron number 11 and element number 11 live in the same part of the cloud. Remember, first 2 columns is my S block. So I write 3S. Since it's an S, it only gets 1 box. I have 2 electrons, so I'm going to do my 2 arrows, but give them an opposite spin. All righty, supermanium. I'm going to come down to the bottom so I have more place to write. Good news is supermanium starts out the same way as the first one. Remember, with D, P, and F sublevels, spread out before you pair up. So up arrow, up arrow, up arrow. Then crap sauce. Down arrow, down arrow, down arrow. I know my down arrows are blending in with my boxes. All right, trying to get all the way to supermanium, which is SU. So I am now at electron number 13, which is 3P. Since I wrote a P, I got to draw 3 boxes. Whether I use all 3 boxes or not, I still got to draw 3 boxes because there's 3 orbitals there. Electrons have choices. I only got 2 electrons to play with because I'm trying to do SU. So electron number 1 goes up, electron number 2 goes up. That is Hund's rule. They don't pair up. They spread out, making their spins as large as possible. As you're doing your arrow diagrams, again, remember, always start at period 1, S block, lowest level. Off bow begins with A. A is the first letter of the alphabet, so we always got to start with the first element first. When you're drawing your boxes, just even if you know you're filling the whole thing up with your P, D, and F, do 1 per box, then pair them up. That way you're in that habit from the beginning. And again, it doesn't matter which way the first arrow faces, just try to be consistent so you don't accidentally violate Hund's rule. So that is it for today. I know it was a lot. We will pick up with this again tomorrow. Make certain you're asking questions in Google Classroom if you need some clarification, but at a minimum, you're going to need a table. You're going to want it labeled with the energy levels and sublevels. So that graphic, that colored graphic that we saw earlier is a great resource to print out and use as you're doing electron configuration. That is it. I will see y'all in the meet.